Hello everyone, my name is Puxin Jiang. I'm a postdoc from the University of Pittsburgh under the supervision of Professor Jeremy Levy. Today my topic is the giant thermal power in quasi-1D quantum wire at the LaLO-SrTiO interface. First of all, what is this LaLO-SrTiO interface? This is an interface between two insulator oxides, lanthanum aluminate, shortened as LaO, and strontium titanate, shortened as SrTiO. Individually, both oxides are insulators. However, when they are put together, the interface becomes electrically conductive with very high electromobility. One interesting property of this LaLO-SrTiO interface is that it has a critical thickness of 4 unit cells for the LaO. This LaLO-SrTiO interface will be conductive only if the LaO thickness is more than 4 unit cells. However, if the LaO thickness is less than 4 unit cells, this interface could be tuned from insulating to conductive by applying a positive voltage and then tuned back to be insulating by applying a negative voltage. Using this fascinating property of the LaLO-SrTiO interface, our group has developed a system using the conductive AFM lithography to write rewritable conductive nanowires at the interface. First, we fabricate the sample so that the LaO thickness is only 3 unit cells. Then this interface is normally insulating. And then we fabricate metal electrodes to form direct electrical contact with the interface. And then we bring a conductive AFM tip to the contact. We apply a positive voltage to write the nanowires. The smallest size could be around 2 nanometers. And we apply a negative voltage to erase the nanowires. This writing and erasing process can be repeated many times, making this a very versatile platform. Our group has conducted many state-of-the-art research work using this platform. Today I'm specifically going to talk about the electrical and the thermoelectric properties of a quasi-1D quantum wire sketched at this LaLO-SrTiO interface. So this quantum wire has a total length of 1.2 micron, and it contains 2 narrow barriers, each with a width of 10 nanometers and separated by a distance of 600 nanometers. So these 2 barriers make it possible for the SiGe gate to tune the chemical potential of this quantum wire, and as a result, we can measure quantized electrical conductance as a function of the SiGe gate voltage. There are also leads on both sides of the main channel to allow us to make the electrical and the thermoelectric measurements. The first step is to measure the 4-terminal electrical conductance. Specifically, we apply a sinusoidal source voltage with an amplitude of 100 microvolt at a frequency of 3.156 Hz to terminal 1, while terminal 2, which is a drain, is grounded. Then we can measure the voltage difference between terminal 3 and 4 at the same frequency, as well as the current, the drain current, and the electrical conductance can be obtained as the current divided by the voltage difference. We measure the electrical conductance as a function of SiGe gate voltage, which is linearly proportional to the chemical potential, mu, at a low temperature of 80 millikelvin in different magnetic fields from -9 to 9 Tesla. So this is one of the typical results. We can see that the conductance increases with chemical potential and decreases with magnetic fields. So in some high magnetic fields, for example 9 Tesla, we see that the electrical conductance increases with steps, which shows the quantized conductance. From the measured conductance, we can calculate transconductance, which is dG d mu. The transconductance map could reveal the band structure of this quantum wire. The bright areas of the map mark the boundaries where new subbands become available. From this transconductance map, we can see that multiple subbands are sometimes locked together, suggesting that those electrons are paired outside the superconducting regime. The next step is to measure the thermal power, which is defined as the voltage difference induced by temperature difference in the absence of any charge current. To measure the thermal power, we first generate a temperature difference. Specifically, we apply the same sinusoidal source voltage to terminal 1, while we apply a drain voltage to terminal 3. We carefully tune the drain voltage, including its amplitude, offset, and phase, so that the potential at the left side of the contour wire is 0. Then no current could flow across the contour wire. Then in this way, we have generated a heat flux at a frequency of 2 omega because of the Joule heating. We can then use a locking amplifier to measure the voltage difference between terminal 3 and 4 at a frequency 2 omega, which is exactly the thermal voltage generated by the temperature difference. With the thermal voltage measured, we still need to know about the temperature difference to calculate the Seebeck coefficient. Here we'll try the Mott relationship, which states that the Seebeck coefficient is proportional to the temperature and proportional to d log g d mu, the energy derivative of logarithmic of conductance. If the Mott relationship applies for a case, then we can calculate the electron temperature by measuring the thermal voltage and measuring the electrical conductance. And then we can put it back to calculate the Seebeck coefficient. Strictly speaking, the Mott relationship works only for non-interacting electron gas. For our case, however, we have shown that we have electron pairs. So we'll see if the Mott relationship still works for us. One specific aspect of the Mott relation is that it states that the thermal voltage should be linearly proportional to d log g d mu. We'll see if this is the case for us. So this is an example of the results we have measured. So we compare the thermal voltage V to omega with d log g d mu in the same plot. We see that they compare quite well with the peaks and the valleys corresponding to each other very well, showing a linear relationship between them, irrespective of the magnetic fields, whether it's 3.5 Tesla when they are electron pairs, or it's 0 Tesla when the contour wire is superconducting. With that, then we can determine the electron temperature, and we plot it out in this figure. We see that when the contour wire is tuned to be insulating state, the temperature difference between electron and the lattice quickly drops to 0. This, however, is not realistic because the temperature difference should always be there, even when the contour wire is tuned to be insulating. This can be explained by a theory provided by Professor Mahan. He suggests that in the insulating state, the thermal voltage we measured should be corrected by a function, a dielectric screening function. And this function approaches 0 when the electron density is 0. So when the contour wire approaches insulating state, we can measure 0 voltage. That does not necessarily mean that the Seebeck coefficient must also be 0. So in this case, we assume a constant electron temperature for the contour wire, and we put it into Seebeck coefficient. Then we can calculate the Seebeck coefficient. We have tested the temperature dependence. So at a fixed magnetic field, repeated measurements at different temperatures from 100 millikelvin to 400 millikelvin, we see that the thermal voltage consistently compare well with the d log g d mu. And when we plot out the Seebeck as a function of temperature, we find that indeed it shows a linear dependence with the temperature. We also checked the effect of source voltage. So ideally, we should use as low a source voltage as possible to minimize the thermal broadening effect. But we still need to use a high enough source voltage to get a high enough signal-to-noise ratio. So if we increase the source voltage, we see that indeed these quantum features are smeared out, but the thermal voltage still compare very well with d log d mu. And if we derive the Seebeck coefficient, they still have the same order of magnitude. We also note that the measured thermal voltage is constant and non-zero when the quantum wire is completely insulating, especially when the source voltage is high. We think that this thermal voltage comes from the intrinsic interface when the interface is completely insulating. We also compare results with the one published in literature, who can measure the thermal power of the 2D electron gas at this interface at a temperature of 4.2 Kelvin. So assuming linear temperature dependence, we convert the results and compare with us, and they compare quite well, which confirms that our measurements could be correct. So to sum up, we have reported 1D, we have measured the electrical and thermoelectric properties of 1D quantum wire. And the electrical conductance is quantized with Pascal sequence, suggesting that we have electron pairs outside the superconducting regime. And we have measured the thermal power. We found that the thermal voltage compare very well with d log d mu, and the Mott relationship works quite well despite the interacting electrons in a quantum wire. And we have derived the Seebeck coefficient, which compare well with the literature measurements, which shows very high Seebeck coefficient, especially in the near insulating state for a quantum wire. Thank you very much.